Okay, so I think we can go ahead and get started. It's good to see everyone here tonight. What I'm doing right now is recording the screen. I'm putting this whole video lecture series online, and I'll be sending out links hopefully the next day after each lecture. Wow, it's great to see you all. Thank you for coming. I think this, I've been wanting to teach a class like this for a long time, and then just one day I was walking on campus and I just went to the registrar's office and they gave me a room. So my name is Randall Briggs. I'm an alum. I graduated 2012, course 2, mechanical engineering. And then 2018, master's in course 2 as well, mechanical engineering. I had a bit of an unusual path through MIT, which I'll go into a bit now. But hopefully that itself is encouraging. But I actually had no hands-on experience when I came to MIT. Unlike a lot of people now who've done FIRST robotics or worked in, worked in different research labs or done quite a bit of hands-on work, I really didn't have basically any experience. So everything that I gained was after coming here. And not only that, it was actually even after I took a break away from MIT, or during that break. So let me go ahead. I'm just going to give you a little bit of my background. The point is not to focus on myself, but only because I think it's useful for understanding why I'm teaching this class and maybe encouraging you too to understand how you can develop a certain amount of proficiency in machining that will help you accomplish your goals. Okay, so like I said, yeah, my first hands-on experience was actually when I got kicked out of MIT. So my undergrad turned out to be 7 years long. Some of you may know the Student Support Services S-cubed office. So when your grades have taken a hit for a couple semesters in a row, they politely ask you to leave, but it's not optional. And it turns out that's actually a really good policy, I found. I think for me, I just needed to mature a bit, just humanly. But really what I needed, and I didn't know it, was I needed perspective. Because when I started my undergraduate experience with 2001, 2002, 2003, which is mechanics of materials 1 and 2, dynamics, controls, all of those classes felt supremely theoretical to me and uninteresting, very boring. And it's not at all, at least to me, it wasn't obvious how that was useful for actually doing something cool. When I came to MIT, my goal was actually to build fighter planes. And I thought about doing course 16 for that reason, which is aeroastro for those who are not from MIT. But what I found out was that even, and this is true of almost any engineering discipline, is that generally mechanical engineers can do a lot of the work. And I'm not saying all of it, but even if you go to Boeing or something like that, you'll have just a few real aeroastro people that are doing the aerodynamics and the airframe and kind of the high-level calculations and simulations. But a lot of it is just nuts and bolts and mechanisms. And so that's kind of what got me interested in course 2. But what I found was that those classes, when we just dive right into the theory and there's no connection to what you can do with it, I have no way to turn that into motivation, personally. And I'm also not the type of person that is that motivated by grades alone. Like, I think I need to see how this is interesting or fun to me. I think most of you are probably that way, and that's kind of what attracted you to science and engineering growing up. So anyway, I took 2 years off, forced by MIT. Turned out to be really good. This was I had a friend actually who had started this company. He was an older gentleman, one of the best mechanical engineers I've ever met. It was called Solero Separations. And they built $500,000 to $1 million high-speed centrifuges for the biotech industry. These were intense machines, like hardcore mechanical engineering. And all of a sudden, all that coursework I had learned became very real. When this machine, when the machine is spinning 20,000 RPM and you don't want it to blow up next to you, the stress and the strain matter, or the dynamics really matter when the vibration starts to go crazy and the machine loses all control. It never happened when I was there, but apparently it did happen once. And the ball bearings from the top of the spindle shot through all the cinder block walls. And fire was emanating from every port of the machine because the bowl was made out of solid titanium. So apparently it was a sight to behold. No one died, no one was killed, or was injured, thankfully. But anyway, yeah, this was great. So I learned a lot during that 2 years. All of a sudden, all my coursework became really real. The other thing, too, is that at that time, it's embarrassing to admit, but I didn't even know what a crescent wrench is, which is just an adjustable wrench. So I had, like I said, no hands-on experience. But they had an in-house machine shop, and it was a small company, about 15 people. Half was machining, half was engineering. So all of a sudden, I got to see the hands-on side, or see how the 3D model that I was building got translated into the real world, and also see how you can go talk to the machinists and learn the problems that they're having with the machine, either with vibration or seals or assembly, and translate that into changes in the design. So it was a great opportunity. The one thing I would say, which was interesting, even at that early stage, was that even though it was such a small company, there was a very clear divide between the white-collar side and the blue-collar side, and they didn't like each other and they didn't talk to each other as little as possible. And it turns out that really was very bad for the company, because the machinists, generally I would actually say the machinists had more knowledge of what was going wrong with the machine, how likely would be the best way to fix it, but they needed to pair that knowledge with the engineers who knew why it was designed a certain way. So a big part of the reason I'm teaching this class is kind of to break down that barrier, so wherever you go, if there is an in-house production facility or prototyping shop with machining, you would not condescend to the machinists. They may get paid less, almost certainly they get paid less than you. In a lot of ways, and they didn't have as much education. But the experience that they have is really invaluable. And on the other hand, what I'm trying to do is actually combine the two people into one person. I don't think there should be engineers and machinists in a sense. To some degree you need that. But ideally, actually, it's an engineer machinist. And you design and build your own parts. Maybe it's just a prototype. But when you do that prototype, you learn so much about how it's made, why it might fail, and then because you're the one that designed it, if you're running into an issue with the machining and it's really hard to make for a certain reason, you can adapt it, and you can adapt the design or adapt the work holding, the fixturing, different parts of it, and because you understand what matters. The machinist may not realize that this particular surface is really important because an O-ring is going to go there and make a seal, but you know that, so you keep that particular surface pristine, but maybe you can put a parting line or imperfection somewhere else. So anyway, during that time away from MIT, I also helped out at Harvard for the Art of Electronics class. This was also great. I highly recommend that basically anyone these days pick up some electronics in addition to mechanical engineering. That may seem like a lot, but honestly, in this day and age of AI, it's not that bad. If you pick up a kit and watch some YouTube videos and go to adafruit.com, honestly, and just get some of their kits and learn this stuff, it's so useful. Even if it's just the basics. If you're able to just work your way around some basic digital and analog electronics, helps you so much. Okay, so when I came back, actually the very first thing I did was the 2007 robotics competition. And this was a cool class because it's individual, so every student gets their own kit of raw materials. And it's raw, it's just a bar of aluminum or tube stock or a sheet of plastic. And you basically have to turn it into a robot. Of course you do get motors, you're not starting from scratch there. But whatever the case, you learn a lot about mechanical design. And it may look easy, but I stayed up till 3 a.m. every day in the computer lab. This is back when you had to run SolidWorks on the MIT's computers and not on your own machine. And anyway, I ended up doing quite well. I really thought about the strategy and about the design of everything. Mine was the only robot that was able to pull the lever all the way over to the 4 multiplier, and I ended up getting first prize, which I wasn't really expecting. And my dad was there, and so that was really exciting because he was really sad when I left MIT, so this made him proud again. Yeah, so he loved me once more. No, I'm just kidding. Yeah, no, he still loved me, but anyway. So when I came back, that win was kind of exciting. It got me a bit of publicity around MIT, and then I opened some other doors. So I worked with Sang-bae Kim on the MIT Cheetah, did some of the mechanical design for the spine and for the tail. Also worked on the electronics. This is the instantaneous power consumption meter that I made. Let's see. I can't go through everything, but anyway, just did lots of hands-on projects. And this was another one that was cool for robotics. This was 212 with Harry Asada. So this was a team effort, but I did the mechanical design of the robot with this really long prismatic actuator and then some other stepper motors. So anyway, we ended up, the software failed, but the hardware worked well, and I got the Best Hardware Design Award. Okay, so anyway, I think that's probably enough about me. I think now I'll transition, or actually, last thing I'll show you is this. Okay, so this was my own startup, which I did for a couple years. Let me try, okay, good, I just want to make sure the audio is off. I made a smart indoor garden for growing fresh herbs in your home year-round. The design worked really well. It looked very beautiful. The lighting was amazing. The plants grew really well. Only problem was, in this case, it was too expensive. That was more of a problem of over-engineering, not so much a problem of design. But just MIT students, we want to measure every variable and control everything. So I went a little overboard for a consumer product. But anyway, I learned a lot. I'm still maybe going to do this on the side, but that's besides that. Well, anyway, the point that I wanted to show you, though, real quick, was when I was doing that, I ended up doing a lot of the machining for that garden in-house, which actually was really useful. And this is kind of where I started to, and honestly, I felt bad about it. I felt like, oh man, I'm just like, I don't have VC capital. I'm just basically family and friends are helping me out. And I felt so bad that I couldn't use a contract manufacturer. But it turned out that I actually learned a lot by making these parts myself. And so, I learned a lot about work holding, which is basically holding the parts down. I learned a lot about cutting, speeds, and feeds. Because my machine was very relatively flimsy and underpowered, it actually made it much harder, which I learned later from a friend of mine who was the head of machining at Neuralink, that actually you learn more when you work with a limited machine. If you jump immediately to a powerful machine, it always works. It's so easy. So that was a good experience. And one takeaway from that, I would say, is I had another friend actually that was doing a startup at the same time. And he told me, so you can see here's like the CAM program, and then you can see how it actually translates to real life. It's basically, it is the same, of course. But one thing that was interesting is that a friend of mine was also doing a startup at that time. And they were contracting out to China. And not that there was anything wrong with their contract manufacturer, but the problem was the disconnect. Both the distance, the language, all these things. So whenever they were running into problems, there was always this arduous job of working through that with communication. And he realized it would have been so much better if, at least for the first production run or the first couple, they had just done it themselves. So if any of you are ever thinking about doing a hardware startup, I would recommend actually doing your own in-house manufacturing as much as possible. That is more and more possible by the day. Partly because these machine tools, which used to cost hundreds of thousands of dollars, are now benchtop and just cost a couple $1,000s. Or you can go to a makerspace and just rent. Or if you're an alum, or a student, you can, of course, there's lots of machine shops on campus, but there's also the hobby shop, which is open to anyone in the MIT community for a paid membership. Okay, so that was great. Actually, the last thing I'll show you is this. This was a part that I made out of a solid block of cast acrylic. And again, I felt bad about this, but it turned out to be a really good way to do it, because these pieces of acrylic cost probably $2. But with so if I had injection molded this, they would have cost, in my lower volume, $5 to $10 anyway, and the mold itself would have cost $50,000. So instead, I just basically had a $5,000 tabletop 5-axis, which I'll bring in, and then made these parts for $2 a piece, basically. So it actually worked out quite well. And I'll just show you. Here's the machine that I used. I'm going to bring this in. I'm hoping that for the practical application in this class, that I can just use my personal machine and put it somewhere at MIT, and you all can try building parts. And sign up for time slots there, so you can see the nice thing about 5-axis in this case was I had features on every side, and I could just come and do that, and it was all accurate relative to itself. So the electrical and the mechanical connectors worked perfectly out of a $2 piece of plastic. Okay, so let's see here. I think because of time, I better jump immediately into the next video, which I wanted to show you. I've got 2 videos, but let me show you the first one. Okay, that is here. So this first one is also from Titans of CNC. This is a really great YouTube channel that I would recommend. They also have a whole series of classes which are really good and go into great depth. This class is going to be more of a broad overview. There's only so much you could teach in 7 lectures, but the idea that what I really wanted to do is expose you to everything. So at least you know what's out there and you can dig in more. Okay, so I may not go into great depth, but at least you understand basically everything, most of what's important in machining. Okay, so let's go to history of machining. Here we go. So this is a great little 8-minute intro. We'll watch this together.
Machinists are the most important of all tradesmen. Without machinists, no other trade would have the tools to do their jobs. Everything you see on a day-to-day basis owes its existence in some way to a machinist and machining, from plastics to clothing to metals to a paper cup. But where did machining come from? My name is Barry Setzer, and I come from a long line of machinists going back at least 4 generations. Our family originated in Germany, and our last name comes from the German word for typesetter or die setter. So you could say that my last name actually means machinist. My father is a master die maker, and I used to spend a lot of time in his machine shop. One day I was looking at his Bridgeport mill, and I asked him how his machines were built if no machines existed to build them. And he told me that machines started off very simple and sloppy, and every subsequent iteration of a machine became better and more accurate and more rigid and more versatile until you get the machine that's in front of you today. That made sense, but where did it all start, and how did we get to this world filled with insane multi-axis machines with axes synced together perfectly, capable of holding tolerances of millionths of an inch? The lathe is an ancient tool and is known as the mother of machine tools. The earliest evidence of turning on a lathe dates back to ancient Egypt and Mycenaean Greece around 1300 BC. Stone carvings clearly show one man rotating a piece of wood using a rope and the other using a sharp object to cut the wood. Yes, lathoglyphics! The lathe remained a pretty simple device for a couple thousand years and was used to make bowls, candlesticks, furniture, sharpen swords, and tons more. Then, hundreds of years later, Leonardo da Vinci invented the first lathe with a slide rest, and in 1718 a Russian engineer also invented a similar lathe, and this was the first major improvement to this ancient technology. A few decades went by, and in 1772 the UK developed a horse-powered lathe used to make stronger, more accurate cannons. These saw a lot of action during the American Revolutionary War and kinda explains why we measure our spindle's power in horsepower to this day. Around this time, people started to use lathes for a process called rotary filing, where you would hold a file in your hand, spin your part in a lathe, and mill material away. The origin of milling machines isn't precisely known, but this is certainly where the process began, and small shops implemented new ideas to push this technology forward. In 1783, the famous London clockmaker Samuel Rahe invented a milling machine, and in 1795, Eli Terry of Connecticut began using a mill to produce wooden clocks. This introduced interchangeable precision parts to the clock industry, which completely changed the way clocks were produced. Between 1814 and 1818, the earliest development of true milling machines took place at the Springfield and Harper's Ferry Federal Armories. During this time, Eli Whitney, who also invented the cotton gin, produced the first true mill, which is the oldest one still in existence. Then in 1860, Brown and Sharp developed a universal milling machine that solved the issue of 3-axis travel, allowing for the milling of spirals like you see in the flutes of a twist drill. During this time, lathes continued to see technological advances as people started to use steam power and insane pulley systems to drive their spindles. If you just Google belt-driven machine shop, you can find some crazy pictures of how these shops function. It doesn't look too safe. By 1936, Rudolph Banno made some major improvements to the mill and called it the Bridgeport. It was small, light, affordable, but also versatile, well-built, and rigid. Over 250,000 of these were built, and almost every machinist has seen one. This was the mill that brought milling to hobbyist garage shops in the world of machining. Then in 1952, numerical control began to develop in the lab and was used pretty much only in a couple aerospace shops. As machinists became aware of this technology, many of them rolled their eyes and said things like, "NC machines are never going to replace manual machinists." But during the 60s and 70s, NC evolved into CNC as data storage and computing evolved. As these machines were implemented, the face of manufacturing changed forever, and this technology continues to develop to this day. While there are still manual machinists out there, CNC absolutely took over manufacturing. Now we have these crazy 9-axis lathes with live tooling and mill spindles, dual turret, dual spindle lathes with live tooling, 5-axis mills that can spin their tables like a lathe, EDMs that vaporize metal with electricity, metal printers, Swiss machines, and thousands of other machines that are just mind-blowing. So, what's next? Well, we're already starting to see some of it. Artificial intelligence that's capable of learning from everyone on Earth and can write its own G-code, augmented reality that can do things like count thousands of parts at a glance, virtual reality worlds where you can slap on a headset and learn how to run a CNC machine in a completely virtual world, nano robots that can build a part one atom at a time. The possibilities are endless. The only question is, will you be one of the naysayers that thinks these technologies won't change the world while you're using your tried and true high-speed steel end mill on your trusty Bridgeport? Or will you be one of the pioneers that embraces the change and helps to develop the future of machining? Thanks for watching. Be sure to check out CNC Expert, our free online academy, and our online store, the platforms we created to help change your shop from the shop of yesterday to the shop of tomorrow.
I would recommend their channel. They have some really cool material, and it's just inspiring too. They do very cool stuff. Okay, so the next, and one thing I just wanted to say too is that the reason I decided to start this class with history is because I think when you look at something as a snapshot in the modern world, it may seem overwhelmingly complicated. But if you look at the progression of it, from, in this case, the dawn of the Industrial Revolution until today, it makes sense. It's actually quite clear. It's like the very first machine tool that really mattered, and it was the one that, I can't remember now if it was Wilkinson, but one of them made a boring machine to bore out the bores for both cannons, but also steam engines. And that was really important because you needed tight tolerances all of a sudden if you're going to have a piston oscillating back and forth. So if you kind of go step by step, it actually makes a lot of sense, and then the leaps are not so great. And then it's more understandable how we get to the modern world. One thing that I wanted to point out, and I'll use the document camera for this, is that actually we have quite a bit of the history of machining right here at MIT. This is a great book that I highly recommend called Numerical Control by, he's no longer with us, but Professor J. Francis Regis. And this is about the servo mechanisms laboratory at MIT, where CNC technology was actually invented. There was the Air Force realized during World War II that a lot of the airfoils that they were making in different parts were quite complex. They had different ways of doing it mechanically, but there was no completely general, adaptable way of cutting a complex curve. And the only way that they could do it at the time was by giving two machinists a table of X, Y coordinates. One would take the X, one would take the Y. They would take turns going to each spot and go down and go down and go down. And then you would end up with a scalloped surface, that had little ridges. That was approximately what you needed, and then you had to shave that, basically smooth it out. So they wanted something that, instead of doing that, would actually coordinate both the X and Y handles in conjunction, kind of like an Etch-a-Sketch. You know how hard it is to do a circle, if you've ever tried that. But if the computer's doing it, it can do, basically to arbitrary accuracy. And so let me show you a couple pictures. So basically, that project began in the 50s, like they said. The Servo Mechanisms Laboratory was born. You took the idea of basically taking a milling machine as they were known, like the Bridgeports, except you replace the X and Y handles with servo motors. And now you have a computer next to it that reads either punch tape or other different types of instructions that are programmed in and goes step by step. The early CNC milling machine, here's the first CNC milling machine at MIT. This was a Cincinnati milling machine, so it was massive. You can see with the computer system, this took up a huge room, cost several millions of dollars, and even in that day and age. But now, of course, you can buy, obviously not the same power, but now we have desktop systems that have all of that technology in a tiny little package, basically on a Raspberry Pi now, or even smaller. So let me go ahead and pass around a couple things. I'll show you real quick. One thing I wanted to point out too is that a common refrain you probably have heard is like, why not just 3D print it? That works for, 3D printers are great, and they've definitely opened up fabrication to so many people that wouldn't have otherwise had access. Even my 3-year-old hasn't started yet, but I'm planning on starting him soon. And it's great for making your own parts and doing things in a pinch. But when it comes to material properties, you cannot get away from the beauty of metal and all the modern alloys that we have. And of course there is metal 3D printing, but the trouble is it's just so expensive and slow. And the surface finish is still oftentimes not what you need, so you often end up having to machine parts of it anyway. I'm going to pass this around. I have no idea what it is. They let me borrow it from the American Precision Museum this morning, but it's a really cool part. This can be made in one operation actually, on a 9-axis mill or 7-axis. You can start it in one side, bore out the whole core, come in with live tooling, cut all these grooves around the outside. Then it leaves a disc here so that it can clamp on this side, holds onto it, comes in, mills this pocket, drills these holes, threads those, puts on the chamfer, and then it comes back and gets rid of this, holds it again on the other side and gets rid of the inside of this disc. And you can kind of see the remains of those operations. And then the last thing I was just going to show is, this was when I was an undergrad, we did the 2670, oh, it's zoomed in too much. Okay, here we go. This was the Stirling engine project, which used to be the case for all mechanical engineers. This was a cool project, but I'll pass this around as well. So I would say that this was all the machining knowledge we were really like directly given in even in Mech E, which should have the most. And it honestly wasn't that much. Most of the time we just went around and like pushed go on the buttons. So we got to design a little bit, but we didn't really learn a huge amount. But it was something. You know, at least it was a starting point. Okay, great. Let me go back to the laptop. And now, yeah, so what I'm going to show you now is this class, every lecture is supposed to have a guest lecture component. I think for maybe 1 or 2 of the lectures, it's going to end up being a video. This morning, I drove up to the American Precision Museum, which is an amazing museum, probably the best. I think it's the best single museum in America, actually, when it comes to the history of machine tools. A lot of that early development happened here, of course, with the Springfield Armory here in Massachusetts. But there in Windsor, Vermont was one of the first real machine shops, machine tool plants. The first factory was actually here in Boston or in Waltham, it's now called the Charles River Museum. But that was the first fully integrated factory in America, and that's where they started doing textiles. But of course, and in the early days, you know, the looms were kind of handmade, but then you started to make those with machine tools. The reason they're called machine tools is because they're tools to make machines. So that's kind of, yeah, the recursion there. Okay, so let's go ahead. What I'm going to show you now is the video I recorded this morning. It is unedited, so it's all in one take, which I think is kind of cool because it feels like you're in the museum. But I'm going to put it at 1.2 speed just so that we can get through it a bit faster. But
Precision Museum in Windsor, Vermont.
Okay, and let me know if it's going too fast or anything like that. But I think that'll be the right speed. We'll see. Let's see how it sounds. Okay, maybe I'll just do 1.1. We'll start there. Hello, good morning.
Good morning.
May I ask for a little intro of who you are and where we are?
My name is Steve D'Alessio. I'm the executive director here at the American Precision Museum in Windsor, Vermont. We're the birthplace of interchangeable parts.
Awesome.
So we'll start our discussion right here on made by hand. If you think about products made in the 1840s, 1830s, they were mostly made by hand. There were some rudimentary machines, but for the most part, you needed a craftsman to manufacture the parts. And in this building, it was built as an armory. So gunsmiths in the local area would be hand manufacturing machines, hand manufacturing rifles. This is our first display made by hand. Here we talk about all the different tools and processes that were used to manufacture a rifle in the 1840s, 1850s. Some of these tools you may recognize being in your grandfather's or father's toolboxes. They look similar to some things that we've used today as well. A few special moments when we were putting this display together was that something we take for granted today, and that's material stock. Round stock or hex stock is readily available. Back then it was not, it was mostly flat stock. So if somebody wanted something round or hex, they'd have to forge it into a cylinder.
Gotcha.
As well. So that's the beginnings. Okay. Along comes, around 1846, along comes 2 gunsmiths, Richard Lawrence and Nicanor Kendall. They're working here in Windsor, right across the river from us. And a third gentleman comes along, his name is Samuel Robbins. Samuel Robbins was a young person who made his money in timbering, mostly in Maine and through Boston. He realized that the government was putting out a tender for 10,000 rifles. And he approached Lawrence and Kendall and said, you know, why don't you guys bid on the job and I'll fund you. But there was a problem with the contract. The contract clearly stated that all the parts had to be interchangeable. So that's where it starts. There were other people around that time working on interchangeability. You know, one was Eli Whitney. Eli Whitney was a better salesman than he was manufacturer, and as a result, he never really achieved true interchangeability. Interchangeability is interesting that, in the sense that if you had a 2-inch hole or a 2-inch bore and you tried to put a 1-inch shaft through it, it would be interchangeable interchangeable all day long. What these guys introduced to the equation was the word precision. That was what it was all about, was how do you create precision interchangeable parts. They realized to do that, they had to take the craftsman's hand off of the part. If you think about a photographer that takes a picture, the same picture twice, there's subtle differences. Same thing with a painter. If he paints the same picture twice, there'll always be subtle differences. And that's the same with manufacturing parts by hand. No matter how hard you try, there'll always be something subtly different about each part. So they realized they had to take the craftsman's hand on it, so that's why we started thinking about made by machine.
Gotcha.
This armory is located right on Millbrook, and there's a reason for that, is that, of course, it's the 1840s, 1850s. Electricity wasn't around just yet, so everything relied on water power. Downstairs in the basement of this building was a wheel pit, or still a wheel pit, but the wheel is no longer there. But the dam was very low, so they had to create what they call a breast wheel. It's a smaller diameter wheel, but very wide. And if you think about a grist mill, the water comes over the top of the wheel and pushes the wheel down. In a breast wheel, the water comes in around the center line and pushes the water underneath the wheel to have it flow. And that's what you see here in this graphic. You see the water coming in through a little bit above center line and pushing the wheel down.
Gotcha.
That was the way they were able to generate enough torque to get the line shaft that you see running throughout the building.
That's something we take for granted now, is that, like, we use electricity to transmit power, but back in the day it was
all
transmitted
water.
mechanically.
It was all water power.
It's like water was the source of the power, but then you had to transmit it mechanically. There was no way to transmit it across a long distance.
Right, exactly. So this is how the whole factory was powered off of this line shaft. If you take a look at this case line, just as an example of what drawings looked like back then, drawings were produced either one-to-one or to some scale, and then the paper was cut around the drawing, so there was no standardization of paper yet like we know today. You can even see the spelling of words have changed a long time, as long as it went. Most of the time they would do it in pencil and then just cover the lines with ink later.
I was going to say, those lines are incredibly crisp and
Yes.
straight.
Yep. So the first of the machines, the first part of a gun that's very critical, is called the lock plate. And the lock plate held the trigger mechanism, the hammer, a bunch of springs, things like that. So as a machine, this isn't very remarkable. It's just a horizontal spindle. But what is pretty special is that they would cast these parts, the lock plate, near net shape. And then the cutter here, because it was now in the right form, would take one pass and cut all the material out, and it would be repeatable because it was being done by machine. No one was hand filing the lock plates anymore.
Gotcha.
So that was one of the first big innovations that took place from this building.
How long would it take to make these custom tools? Or
I don't know. I'm really quite amazed at it myself. I know how to do it in today's technology,
Yeah, right.
but back then I don't know how they did it exactly. What I do think is that they didn't know a lot about metallurgy at that point in time, but they did know if they heated a part up and added some carbon to it,
Gotcha.
and quenched it in some kind of animal fat maybe or an oil, it would get harder. That's what they knew, and it would give them more longevity. The next machine in the progression here is, once you have a lock plate, it has to mount to a gun stock in a very accurate form. But the pocket in the gun stock had to have multiple depths to it. So here they would now stack up a bunch of patterns on top of each other. Each pattern would be a different layer in the gun stock. This probe would follow the pattern, and the cutter goes along for the ride.
wow, at fixed depths.
At fixed depths.
Gotcha. Wow.
Then the belt would move from this position here up to here, which is now an idling position. And the operator would take this mechanism and index the whole thing to bring another probe in, another cutter to pick up a different spot on the pattern stack.
Gotcha.
This becomes the beginning of tool changing.
Oh, okay.
So
In this case, it's just different diameter tools, or is it?
It's different probes in different diameters. So this whole mechanism with this belt in the idling position, this mechanism would be able to index over and be able to pick up a different. So this is like one of the first and early examples of tool changing, which led us to today's technology of automatic tool changing.
Right.
This machine also had bellows in it to blow the chips out of the way, to get it off the operator. elevator.
Were those just like a foot pedal powered or something?
No, it was powered through the water power, again, through the
Gotcha.
belt system.
Oh, automatic bellows,
It
wow.
would be bellows as well.
Okay.
This was manufactured in 1850 by the Ames Manufacturing Company out of Chicopee, Mass.
Awesome. It's beautiful.
One of the things that Robbins and Lawrence did is they went around the Precision Valley, or this whole Connecticut River Valley, and collected some of the best technologies
Gotcha.
that they could find and brought it all together in one process. Again, all working to take the craftsman's hand off of the parts.
So would you say that they invented much themselves, or was it more that they were integrators, that they kind of put everything together? And...
I would say they're half inventors, half integrators.
Okay. I guess you could say sometimes integration is the invention, huh?
Well, instead of integrator, I like to say innovators.
Innovator, okay.
Right, because inventors start from a whole brand new perspective, I guess.
Right.
And an innovator keeps the constant improvement on what's existing.
Sees what's next.
Sees what's next
Gotcha.
in the improvement line.
Cool.
The next machine in the world, in our world of making guns is the rifling machine, which puts the spiral inside of a barrel. This is a small example of what it would look like. You'll see the spiral there. This machine is set up for a pistol or a very short barrel. Based on its geometry, would determine whether or not it would be a very fast spiral or a very slow spiral. There is an indexing plate on the back side, and the indexing plate would determine how many interleaving spirals there are. There's a cutter here. When it came out of the barrel, it would bump up against here and would be indexed out. So it would progressively get a little deeper. Awesome. This machine was also equipped with this nice handle here, so if water power ever stopped, they'd probably put a young laborer in front of this to keep this thing going all day long.
Good arms workout, huh?
Get a good workout for sure. The next piece of us in our line of machines is this lathe for turning irregular shaped parts. It was invented by Thomas Blanchard, and he got the idea out of a set of French encyclopedias for turning irregular shaped parts.
Was that Diderot's?
Diderot's.
Wow, it was. Okay.
Yep. So you'll see again, the object is to get the craftsman's hands off of the part.
Yeah.
Here now you have a metal pattern. This wheel would follow the pattern, and it would take this cutter and bring it into the wood and be able to turn the stock.
Gotcha.
You can get kind of a feel for.
And then would it have to be like hand sanded after this?
Probably.
Okay.
They probably did some kind of handwork afterwards.
Gotcha.
But so the real question as we get here now is why?
Right.
Why should we bother with all this, right?
Yeah.
We were able to make guns before, we can still make guns today.
Yeah.
But the first benefit of all the work that these guys put in was for part accuracy. Here we're trying to take that craftsman's hand off the part and let the machines do the work.
Gotcha.
So that was the first real big benefit. The second big benefit was process improvement. Making parts by hand was very labor intensive. By making machines do the work, we reduced the labor. If you look at here, you'll see that it took 115 hours to produce one rifle, and now it was brought down to 31 hours, and the most of it was with the gun stock. You can see where it took 22 hours to manufacture a gun stock, and now with this machine that we just looked at, it got down to 2 hours.
Remarkable. And automated too, so it was basically unattended, or did someone have to stand?
There was somebody probably near the machine or around the machine.
But they didn't have to be skilled
They
necessarily.
didn't have to be skilled because the machine was doing the work now.
That's awesome.
So our next piece of this, the benefit, right?
Yeah.
One of the real benefits had nothing really to do with the machines, but it really had to do with the community. Factories were the center of communities back then. They would hold picnics, they would do concerts, they would do all these things for the employees, and that again created a better lifestyle for those in those communities. They formed relationships with local businesses. I always said back then, if you found a factory back then, you'd find a barber nearby, right? And today I always say, if you want to know how well a company is taking care of their employees and providing for the community, just walk through the parking lot and see the level of cars in the parking lot, right?
True.
You'd probably see a lot newer cars in a good factory than you would in a poor factory. So we also know that machine design created a lot of efficiencies. Here, if you have a single spindle drill press and you pull a handle, you get one hole, one spindle, one hole. With the same amount of energy of pulling a handle, if you had multiple spindles, you now can get multiple holes. So you see a big jump in efficiency now taking place as well.
And that was all around the same time?
You're all around 1840s to 1850s. Here we just show process. Like in the case of this multi-spindle drill press, they could have multiple tools in it.
Gotcha.
And
several steps left for one hole.
Step one, it could drill the hole. Step two can make it bigger, ream it, counterbore it, and tap it. I mean, it's just basic machining. Here's another multi-spindle drill press. This one was invented here. It's a 6-spindle drill press. All the depths would be adjusted by these spindles up on the top. And either you stepped on the pedal or pulled the handle, and the table would go up.
Gotcha. And now with tapping though, now all of a sudden the vertical movement has to be synced with the rotation.
I don't think they did tapping in these machines.
Okay, gotcha.
Just for that reason. How do you sync the rotation with the feed?
Okay.
I don't know. There is an example of some external threading that we have. So we fast forward now to 1851. It's the Crystal Palace exhibition, the great exhibition of industrial works. These guys are invited to go there. They bring 10 sets of parts and throw them on the table, and the Brits are absolutely amazed that they can interchange all the parts. They can just go to the bin, pull out a hammer, pull out this, pull out that, and they would all fit together without any hand filing or hand fitting. The Brits promptly placed another order for 10,000 more rifles. But more importantly, from the 1851, is the Brits wanted the machines. They wanted the process. And they coined the phrase, the American system of manufacturing, which is, again, allowing the machines to do the work.
It's interesting because I remember learning at the Charles River Museum about how when it came to the loom that we kind of did some industrial espionage and brought the loom from England,
right?
Brought the design over, but in this case, I guess we really had innovated. We had now kind of surpassed them in a sense.
Yes, the French and British were actually moving in their direction of interchangeability.
Gotcha.
It was Jefferson that came over and said, "Hey guys, we got to be doing this."
Okay.
And then the government and the armories, private armories, formed a partnership to allow it to move forward in a faster pace.
Gotcha.
By putting that clause in the contracts.
Right.
My understanding is that there's a similar clause even in today's contracts as well.
Interesting.
So the Connecticut River, something happens in 1855, 1856, Robbins and Lawrence overexpand and they close. But not before the American system of manufacturing goes down the Connecticut River. People that were trained here at Robbins and Lawrence wind up at Sharps. They wind up at Brown and Sharp. They round up at Colt. They wound up at all different places up and down the river. So the American system of manufacturing now begins to travel up and down the Connecticut River. The Connecticut River area from Windsor down to New Haven and Hartford becomes known as the Precision Valley.
So even back then, they called it Precision Valley?
Precision Valley.
Okay. Cool.
So now we know we've gone from made by hand to made by machine. Now the next step is really machines that make more machines. And that's where we jump a little bit in time. We're up to around 1938, 1930s. Bridgeport, Rudy Bano invents the Bridgeport milling machine, which of course is iconic. It's everywhere. I'll put a plug in for this guy here. This is serial number 1, Bridgeport from 1938.
And how did you all get this machine?
This one was here before I got here. So
okay, gotcha.
I think my understanding was out in Ohio somewhere, and it was moved here. But more impressive than serial number 1 is this guy here. This has no serial numbers on it. It was taken off of the production line and sent to Rudy Bano's house. So the hand of the inventor of the Bridgeport was on this machine making parts in his basement. So this was another very unique machine.
What was the main innovation of the Bridgeport compared to prior machines, would you say?
Bridgeport initially made only the heads. Okay. They only made this mechanism here.
Gotcha.
And that was used to be mounted on different kinds of machines. Okay. So what really was the innovation here was integrating it all together, adding precision lead screws to the machine. So now suddenly you can manually machine in a very accurate way.
Okay, so before that, it was kind of open loop, you could say?
Open loop, right.
But now you could actually look at the dials.
Now you can actually see the dial and split a thousandth here.
Gotcha, okay.
You can do things like that.
Gotcha.
So the big innovation was the integration of all the technology into one place. One of the things that we know, of course, is to make machines, you need very flat parts. So we created planers. This is around 1845. Planer would come along just like a wood plane today, scrape the top of the material. When the table reversed, it would kick the cutter out of the way and just keep going back and forth all day long. And that would create very flat surfaces. I will point out this machine has a lot of fancy scroll work or gingerbread kind of things on handles and up here as well. Two schools of thought exist. One is that carpenters were the pattern makers of the time, and the machine tool builders may have wanted to let the carpenters put their own touches on the machines. The other theory is that it's the Victorian age of design, and maybe that's slipping into the machine tool world as well.
Beautiful.
Some other things in our collection of interest is these Surveyor's Transit and Sextant.
Oh, beautiful.
They're 1930s or early 1900s, just to show the beauty of manual machining that could take place. Or rudimentary.
So they were precision parts, or precision mechanisms, I guess. But,
yes, back then as well.
Machine by hand,
yeah,
not before
right.
it first predates CNC. Wow.
Right.
That's impressive because I think that William Barton Rogers, the founder of MIT, was a geologist.
Yes.
And that's kind of, so he wanted, part of the reason why he made the MIT motto, mind and hand, is because he wanted people that could actually use the tools, not just had the theory about geology.
Exactly. There are some true artifacts here in the museum. This is one of them. Gauge blocks were invented around 1896 or 95 by a Swede named Johansson. That's where we get the term Joe block from. Henry Ford enjoyed Johansson very much, so he bought his company. This particular set of gauge blocks were produced in a Ford factory. And Henry Ford really enjoyed Thomas Edison a lot. They went camping together, they traveled together. So this particular set in this case line was given from Henry Ford to Thomas Edison. It came out of Edison's labs in Menlo Park. So true artifact. Here we have examples of measurement that we do all over time. Again, nothing really, it's just to show that we measure things, right? And part of, if you can't control it, the only way to control something is if you can measure it, right? And that's part of precision manufacturing. So that's what we're trying to explain here, that, you know, we measure speed. So how does that work? And how do we measure time and so forth? So all those things go into creating precision parts.
Could you show me the supermicrometer?
Yep. This is one of the things is measuring distance, of course. And here we have a supermicrometer from Brown and Sharp. It's around 1878. Very fine gradients on the wheel and along here, graduations. And it's still good to probably about 10 millionths of an inch.
Remarkable.
Another nice, interesting artifact that we have is it's nothing more than a protractor. So the challenge always is, how did they get it together to stay together? And we looked at the geometry of it, and we feel that this geometry allowed them to compress it, slide it together, let it go, and it would lock in place. There's a little spline along here that would allow it to rotate. For that to be true, this would have had to be made of spring steel. And very recently, we found in our collection the original manufacturing drawing of it, and even the drawing specifies spring steel on the drawing. So we try to connect the physical object with the paper documents here to provide some sort of provenance to what we're thinking about. This is a really big lathe that you see this here. We know that it was designed to be manufacturing something larger than it was designed for because of these riser blocks that you see in the tailstock, the carriage, and the headstock. One theory is that they would take the line shaft, put all the pulleys on it, put it between centers, and then true up each pulley so that everything would run concentric. Because you can imagine if a pulley wasn't concentric on the line shaft to another one would get tight and the other one would get loose as it was running. So that was one theory that we have about this lathe. It is one continuous casting. It was manufactured here in Windsor, Vermont. The museum isn't always about old machines. We do have some newer things. We try to introduce young people to 3D printing and other forms of computer numerical control machines, as well as some robotics. As well as we go around, we'll see more of that. But the idea is to create. The purpose of the museum and its mission, very simply put, is to inspire the next generation, right?
Awesome.
Innovators, inventors, makers, on the backdrop of history. It's really important for people to understand that we went from made by hand to made by machine through patterns and so forth. And then as the world innovated and things like CNC and numerical control started to come into play, we just kept on improving until we are today. Some other machines in our collection, very large shaper, vertical shaper, works similar to a planer, only going up and down, mostly for putting keys and keyways into large pulleys and so forth. Other machines like turret lathes and things begin to get invented as well. And now we're really into the late 1800s, early 1900s as well. This is a replica of the model of the water wheel down in the basement. Again, you can see the gear here was too large to cut all at once, so they made segments. And there would be a main wheel and then a drum connected by a pinion, and from the drum, all the belts would travel through the building. There's a gear segment down there on the bottom.
Yeah, look at that. One of the original pieces, huh?
Well, we're not 100% sure, but it was found in the building. So
okay, gotcha.
I will. So, all the bright young students down at MIT, we don't know what this machine does, but you can see it. It has lots of different functions. So we're always looking give everybody a challenge to help us find out what this machine is.
Okay, that is a curious challenge. Look at that. Do you know the time frame when it was built?
Not at all.
Okay.
Probably, I'm going to say early 1900s, but
okay,
not sure. As I mentioned before, there was a planer, and this planer is about 20 years older than the one that we just looked at. But you can see that the shape is pretty square. There's no fancy scroll work or anything on it, but the machines both do the same exact thing.
Gotcha.
So it's interesting to see just the change in 20 years in design. Another gentleman comes along. His name is Frederick Howe. Frederick Howe was a great inventor. Worked for Robbins and Lawrence, worked for Brown and Sharp. He may have even gone to Pratt and Whitney at some point in time. So he just invented a lot of these machines that you see here. This is a universal milling machine based on these holes, and you're moving a lever would turn the angle of the vise in different directions. And then the cutter would come across. You could do lots of different things with it. By pulling out the drift pin, you can remove the chuck and put a different, more of a round chuck or another indexing and dividing head. Again, turret lathe. Thing to remember about a turret lathe, it's still only one tool, one spindle.
Right.
We'll talk a little bit about another gentleman that had a different idea. Another universal milling machine. Here is a threading machine. They'd put round stock in here, push the die on it, it would self-feed, and then it would reverse it, and this would be self-feed out. So it's now late 1850s, 56, 57. World's wars begin to end. So what do you do with your factory that's been tooled up for rifle manufacturing? You enter the world of the consumer culture. But you enter the world of consumer culture to make sewing machines, typewriters, kitchen gadgets, with all of the knowledge that you learned from the American system of manufacture. You learned how to make parts by machine, and all that led to lower cost of manufacture, which now allowed the masses to have more of these items like watches and kitchen gadgets and sewing machines and so forth. And that really just changed how America worked. Right? So we do have some examples of our early high production machines. This is pocket watches in the 1890s, early 1900s, become all the rage. And this machine here, work would take place, then this arm would pick up the screw, take it over, and slice the head of the screw.
Awesome.
Drop the screw down into the little bucket down there. So this introduced another type of technology, cams and cam followers. Now we're able to change rotary motion into linear motion, and that became another big step in what we're doing. Another machine. And of course, now we start doing typewriters and sewing machines. The Clark's revolving looper over here was the first practical sewing machine that was invented here in this building.
Really, in this building?
Yes.
Wow. And they made them here?
Yeah, under a different name.
Okay.
If you needed bigger parts, we manufactured, you just create bigger machines. Then comes along another guy, his name is James Hartness. James Hartness invents the optical comparator. They realized that in order to measure things precisely, they needed to blow them up, so in this way they can magnify it and start seeing small changes in a bigger screen and see small changes, particularly geared for screw threads. Screw threads are complicated in shape, and if they're not cut correctly, they just don't work very well. More examples of things that were manufactured.
Is that a Norton bomb site?
That's a Norton bomb site, right?
Those were also made up here? Or just machined in general?
Just machined in general and precision. Understanding that after the war they destroyed most of them so that no one would be able to get the technology. Here again we using examples of cams and cam followers.
Awesome.
Another machine here from Springfield, Vermont, Bryant Grinder. This is an ID/OD grinder.
So the difference between a grinder and like a milling machine is the fact that it uses a small abrasive and like a relatively smooth surface? Or?
Yeah, a grinder uses an abrasive to remove material.
Gotcha.
A milling machine uses a cutter of some sort.
Gotcha. And the grinders are always for getting a finer surface fit or greater accuracy or greater precision, I guess.
In general terms, yeah. I mean, there are other machines.
Yeah.
There's creep-free grinding, and there's other technologies today that are used for roughing complex shapes and so forth. Gotcha. That could also be done with grinding.
Gotcha.
So as I mentioned before, turret lathes were one spindle, one tool. A gentleman named Frank Cohn had a different idea here in Windsor. He said, if we bring in all the tools at one time onto the spindles, then you'll wind up with one part every rotation of multiple spindles. Gotcha. So sort of like the drill press. They added more spindles as opposed to more tools.
Gotcha.
So this machine, 4 tools come in at once, and the part comes out finished after each time the tools come together.
Would you call this a predecessor to the Swiss lathes then?
Yes.
That have multiple tools? Okay.
This is a predecessor. Gotcha. Except today's Swiss machines still only have one spindle.
Okay.
But they change tools so fast and rapidly that it's not the same. But today there's still some multi-spindle machines out there that are still used.
And by multi-spindle, you mean there's more than one part being made at a time?
Yes.
Or one part's going through different segments?
Segments based on spindles. So it should be, in this case, there's 4 different spindles.
4 spindles, gotcha.
Right. And this time when the tools come in, each tool does a different segment of it at one time.
Okay. And then you have to manually switch the part from one spindle to the next?
No, it does it automatically.
It's automatically, okay, cool.
So we're also trying to show people automation. So we have a thank you to Universal Robots for
very cool.
donating a robot to us, and along with Fanuc as well.
Nice.
Gossenger Automation graciously donated this guy to us as well.
And now, I've heard of course robots being used in changing, putting parts right into machines, pulling them out.
Yeah.
Is it called automatic pallet?
No, there's just robotic feeding.
Robotic feeding. Okay.
Yeah. Parts feeding.
Cool.
Eventually, in our broad plan is that these robots will be moved to machine tending, putting parts in and out of machines.
Cool.
In the middle here, we have the innovation station. It includes a vertical CNC milling machine from Haas. Same thing with the CNC lathe from Haas. Pallet changer from Idaco.
Okay. So the pallet changer, I see. This is so that you can prep one piece while the other one is machining?
Machining, right, and then the door would open and swap the pallets.
Gotcha.
This machine is also equipped with 2 other technologies. One is it's got a probe that comes down and touches off the parts. Again, the whole idea is to take that craftsman's hand off of the part, right? So if we can now we've replaced it with this probe to do that as well. It also has a technology from Chiron Engineering. You'll see a little sensor mounted to the spindle that's looking at the vibration in the spindle and in the machine. So if a tool is getting dull, the spindle has more vibration in it. Now we can start detecting it before catastrophic failure happens.
Gotcha.
We also have a CNC lathe from Haas, and it's tooled up with Kennametal tooling and Iskar tooling. Again, we're here to show now the progression from made by hand, made by machine, now to what we're doing today.
Remarkable. And now with the vibration sensor, would that also be used to kind of detect chatter from other reasons or from other causes? Or I guess by then you would assume the program's been...
Once the machine starts vibrating, then you've got issues.
Whatever it is.
The reason.
Gotcha,
right.
okay.
That machine also has another piece of software from Chiron called AutoComp. So if you measure a part with a micrometer or a caliper, it'll send that information to the control and do automatic cutter compensation for it.
Based on tool wear?
Based on tool wear or whatever.
Whatever it is, okay.
Whatever it is.
Awesome.
We also have another piece of measurement equipment here, donated by Renishaw.
This one's amazing. And what is the accuracy or repeatability of this measurement device?
I would say under 10 millionths.
Okay. Amazing.
This is a comparative CMM.
Okay.
So it's comparing the part that was manufactured to a master.
Okay.
And that uses the same probe that we use on the milling center for setting up the machine as well.
Awesome. Beautiful.
So that's where we are.
Okay.
That's our great little museum here in Windsor, Vermont.
Thank you so much. I really appreciate it.
It's all about inspiring that next generation on the backdrop of history.
Well, hello from MIT. We really appreciate it. I'm sure the students will love it.
Thank you.
Bye-bye. Awesome. In fact, I was thinking to thank Steve for recording that video with me this morning. Maybe we could all say thank you as a class. Let me turn on my camera, and I'll just show him all these beautiful people. Can we all say thank you, Steve?
Thank you. Thank you, thank you.
Sometimes when you're talking to a camera, you don't see all the people that it's going to affect. And of course, this is just a small percentage. We actually had, I posted this class on X, and we had over 600 people sign up. So there's a lot of demand actually for this kind of material. One thing that I realized is that what I wanted to get to the heart of in this class is the basic principles that drive everything. Because there's unending complexity in the machining world, unending details, unending books and reference works. You could spend the rest of your life learning everything, but the basic principles don't change. And one of the basic principles is basically work holding, so that means holding the part that's being machined rigidly. And what I mean by rigidly is rigid relative to the cutting tool. So it's called a structural loop. So whatever's holding it in all the mechanical connections between that bed and the actual spindle, because that's what matters. And then the other basic idea is that this tool is removing material through shear, basically causing plastic deformation, failing the material, and taking chips away one at a time. Whether it be a lathe where the part is rotating and the tool is kind of just going along slowly and taking a long chip, or many chips, or it's a mill where it's a turning cutter and it's going through. So that's the basic idea. So what you really want is rigidity between your part and your cutting tool, and then you want to choose the right tool for the job, for the geometry that you're trying to cut. But gosh, that's about it. And like everything else is just kind of details. But okay, let me go through a couple other things. One thing I wanted to say too is that I think MIT is a special place to teach this kind of class because of our heritage. I think we take it for granted now because every school has actually sort of adopted the MIT style. I know you don't realize this, but when William Barton Rogers started MIT, of course Harvard was the big dog right in town, and but if you were a student in Harvard at that time, your time was spent learning ancient Greek, ancient Hebrew, Syriac, Latin, and reading all of the classics, reading philosophy, and maybe understanding science. You know, you would understand some basic science. Even then, it probably wasn't hands-on. We were most likely reading about science. So what William Barton Rogers realized was, and why he made the motto mind and hand, is that he was finding that so many of the students that he found, and because he was a geologist by trade, understood theory and understood literature and classics, but could not operate tools or innovate, or really were not that useful in the field. So the whole point about MIT was that you do both. You do the hands-on classroom learning, or laboratory, or even field learning, and you learn the theory. And those together is a very powerful combination. We take it for granted because that's honestly everywhere now, even at Harvard now. They're putting a lot of investment into their engineering program, and which is getting quite good. So. Yeah, it's like I just wanted to point that out. That actually, we're so used to what we have today, but it's actually in terms of history unusual. Okay, and the other thing I was going to say is part of the reason that William Barton Rogers had that insight was that he realized that when you work with your hands, it's very different from learning from a book. There are so many things that are unspoken or very hard to communicate besides just literally feeling it yourself. And for that reason, I would encourage you when you begin your machining journey to actually do some manual machining. And this is just mostly for the learning of it. Sometimes it's actually useful, but like literally turn on a Bridgeport like he showed with the end mill, have it cut some aluminum, feel it, and listen, because those are honestly, with a CNC machine, you no longer have the feel. The machine is doing its thing. So all you have left is your ears, and you can hear the vibration. You can hear that it sounds right, and it's subtle, but the more you do it, the more you'll get used to it. And this is part of the reason I think that mechanical engineering is somewhat safe from AI, at least if you're doing the actual machine designing work, is because there's no way to really put these things into books. It's sort of in videos, but like when it comes to actually feeling the friction of something or feeling like the play or the vibration, you can measure it. I don't know. It's just like, I believe AI will get there, but I think we got at least a little more runway. So the more hands-on you can be these days, the better. Another reason why I really want to teach this class right now is because there is, if you've not seen in the news, there is a massive shift of manufacturing coming back to the United States. For many years now, we've been sending manufacturing abroad, mostly to China, which is not altogether a bad thing by any means, and I'm very happy that the Chinese people have been lifted up in their well-being. But the trouble is that we've hollowed out a lot of our key industries, which are really important, both for national security, but also just for our health of our economy and our resilience. We saw that during COVID, when supply chains really got shocked, and all of a sudden we couldn't make any of our own stuff, and we had to kind of air freight things from abroad in an emergency kind of way. But whatever the case, because of the CHIPS Act as well as the Inflation Reduction Act, there's a lot of money being put into reindustrializing this country. And the amount of money being spent on manufacturing construction is at an all-time, I can't remember if it's all-time high or at least highest in many decades. So you're going to see that whichever companies you go to after MIT or wherever you are, there's going to be a trend of bringing manufacturing back. In fact, I saw in Forbes, it said recently that 70% of companies in the US that currently manufacture in China are actively bringing back some portion of their manufacturing to the United States. Partly for geopolitical reasons, partly for, there's many reasons, but for the tensions and different things too. But fundamentally, I just think that there's no replacement for being able to walk to the machine shop floor or the factory floor, as the engineer, see how it's being made, see what the problems are, talk to the machinist, get that feedback, even hear it yourself, or see the little, maybe vibration or the imperfections that are occurring, and then you can go back and figure out how to change it. This is part of the reason, I don't know if you've heard, but Elon Musk, when he was designing the original SpaceX facility in Hawthorne, he put the engineering offices actually right in the middle of the machine shop. So it was the production facility, and there was literally like stilts and like an office like above the machine shop floor, so that every time the engineers wanted to go to the bathroom or go get lunch or something, they had to walk through the. Did you say something? Oh, sorry, I just said something. But anyway, yeah, so they had to walk through and talk to the people. And so by design, it was forced. That actually was the case at Bell Laboratories, too. They purposefully jumbled all the offices and everything up so that people had to walk in the hallways and have chance meetings. But whatever the case, the point is, there's a lot of chemistry that can happen when you are close to the production facility. Of course, even if it's in China, a lot of times you'll be, like if you work at Apple, you're flying back and forth, and you're in production, you're flying to China like every month at least, to talk to the engineers there and make sure things are being made properly. Okay, so my job here as an educator is really to kind of open the world to you, give you a toolbox of information and concepts that you can take to that you can take as a starting point to go off and learn really yourself. But I would say the number one job is actually for me to impart motivation into you of why this is important. You being here is already a great sign. That shows that you value this class, especially because it's not for credit. That's actually really amazing that you're here at all. But what I really want to do is just explain to you or impart to you why this is so valuable, how it will help you in your long-term kind of journey as a designer, and honestly, whatever background you are, whether it's chemical engineering or biology or mechanical engineering or nuclear, like it really helps to understand how things are made from so many different angles, and you will be a better designer for it. Or even if you're just in chemistry and you're going off to do a postdoc, and you can make your own bracket. You can make something, custom piece of equipment to handle your experiment, whatever it may be. It really empowers you to be able to build things. It feels good. It's like cooking or something too. So with that in mind, what you need to do, I work full-time. So I actually work at a humanoid robotics company here in Kendall Square, which is really cool. But I unfortunately cannot really lead laboratories during the day. I'm hoping that I can find a place to put my 5-axis tool so that you guys can kind of pair up and do a project on that. But what I wanted to show you actually is that we are so fortunate to be at a place like MIT where we have access to so many machine shops. It's crazy. Okay, so if you go to make.mit.edu, I think, yep, that's right. You can go to find a makerspace here, and it's just like mind-boggling how many we have. And I'll just give you a personal kind of tidbit. Like, for example, I often study. There's some really nice tables in building 6C, that kind of awkward building in the middle of the courtyard. And when I study there, you have a clear view of the physics machine shop. I've studied there for, I don't know, almost 20 years now. And I've only seen that machine shop being used like once, maybe, and that long. So there's and I've talked to a lot of the machinists on campus, and there's really quite an underutilization of all the resources that we have. So my goal is basically to inspire you to go out, look at this list of makerspaces, like find one that's useful, or has the tools that you're interested in, and talk to the technicians, learn from them, get trained on the equipment, and then build stuff that's interesting to you. The best way to learn is just to build. And it may seem intimidating to get started, but just talk to the machinists. A lot of times they might even have a kind of a structured training program. But whatever the case, just get out there and make something. Go on YouTube, follow some kit if you wanted to. But yeah, and so I'm going to do some prizes. Okay. So I bought some trinkets from the American Precision Museum. So these are some cool parts that they made in the house that are locked in place. It was made out of one block of aluminum, and there was this little insert that's locked inside. So this is going to be first prize. We'll get a T-shirt for the American Precision Museum, which is home of the first Bridgeport. So you can proudly wear this around campus. And then, yeah, second and third place will get this. And the goal is basically just whoever shows me that they've taken the most initiative to go out and start learning, in whatever form that takes. If you're not part of the MIT community, there is Artisans Asylum in Somerville, I believe. They're still operating, and other makerspaces in the Boston area where you can go and pay a subscription or get involved. Okay, yeah, I think that, let me see. Now, I've got just a couple other bits of administrative stuff. Okay, so those are the prizes. Oh yeah, okay. Gosh, I'm like a little sad to do this, but this is my personal set of calipers, Mitutoyo calipers. These are basically the best ones out there. Digital calipers. They have a tungsten carbide jaws so that you can measure very hard or abrasive material and it generally won't even affect them. I decided that I will give these to the student that just generally impresses me the most with how much you've done in this 1 month period. So at the end of the month, I'm gonna just come to me and show me what you've done, and I will give this to the one that impresses me the most. Also an excuse for me to buy a new pair. Yeah. Okay, and then next lecture is going to be on Wednesday, 6 p.m. here as well. I think that it will also be, the guest lecture will be a machine shop in Connecticut, which does some amazing aerospace parts. And then, hopefully I'll have more information for you at that time about the hands-on component and whether or not we can use my 5-axis mill. If there's any questions, now would be a great time. I've got this microphone so that we can record it. Is there anyone that has any questions about anything? Okay, yeah, here we go.
What's the best way to get hands-on experience at MIT without getting kicked out?
Okay, well, actually, that's a good question. And I would say that what worked for me, actually, and I forgot to mention this, was joining in clubs. So I joined FSAE, which is the Formula race car team, which was really good. And you get a lot of hands-on experience if you join that one. There's also electric vehicle team, which also operates in Area 51. These are all part of the Edgerton Center, so they are open to all of MIT. You don't have to be in mechanical engineering. There's Rocket Club. There's the D Lab that does like more international stuff. There's different classes where you can build things. That's a great way to do it too. Actually, a really good class in course 2. I think it's both a graduate and undergraduate class. It's 272 with Marty Culpepper. I think it's called Precision Machine Design. That probably is the most relevant class. It's pretty hardcore, or I should say it's moderately hardcore. You actually make a lathe, a miniature lathe. At least that's what I did. I think that's what they still do. So that's a very good resource. So I would say pick classes that do have the hands-on component. They are a little bit more rare than they should be, I think. I honestly feel like kids should learn how to mill from like the time they're 5 or 6. I don't know. And this was the case with my professor, actually, Ian Hunter. He and his brother, his dad was an inventor, kind of a crazy guy, and he and his brother each got their own machine shop when they were like 5 and 6 years old, and their own chemistry lab. So they each had their, separately. And they almost lost their fingers and different things, but they survived, and they learned, and now they're just incredibly brilliant people. Yeah, sorry. Your shirt's on. Here you go.
This is awesome. I love this.
You. Yeah.
Do you know if any of these, before I do a 3-hour search on all these, do any of these have MIT IAP like tours or little classes that you already know about before I spend my 3 hours searching through every single one of these?
Yeah.
And then my second follow-up question is, I have 11-year-old twins, and I would love to bring them. They actually wanted to come tonight. I made them go to bed. So I'm glad you recorded it. But do you know if any of these allow 11-year-old kids in them? Those are my two separate questions.
Good question. Yeah, I think I don't know. The only one, the most likely one would be the hobby shop. I don't know where it is here. The hobby shop is open to all MIT alum. Anyone in the community or past community can pay, basically pay to be part of it. The hobby shop, I think, does have regular classes going on. They're probably doing some during IAP. The other one that's really good is the Edgerton Machine Shop that is in Building 6 with Mark Bellinger. He'll be one of the guest lecturers as well. I'm sorry, I don't know where it is on this list actually, but that one's also great. EDS. I think it's, here it is, Edgerton Student Shop, 6C-006A. And then there's the hobby shop, if it's here too. There's the hobby shop. So that's over in Area N51 now. So those are probably your best bets, at least for the general MIT community. Any other questions?
Any IAP classes teaching us about any of these? People know about or you know about?
Well, I think that the Edgerton shop probably will have something. Yeah, I think those are the two that were most likely. I don't know of any other specific ones. If anyone else knows any.
I know that in future for the morning.
Sorry.
The MAD one, it's like Morning Design Academy. That one has IAP classes, and I think you can just if you search MAD IAP, it anyone can see the list of classes, and then it has a contact that you can reach out to.
Oh, nice. Okay, that's good to know too. Okay, great. Any other questions? Okay, yeah.
You mentioned a large influx of manufacturing in America.
Right.
What do you foresee being the largest expansive market for manufacturing in America? Do you have an opinion on that?
Like which part, which subcategory?
Which industry
I think it's going to be all kinds. Actually, one of the biggest ones might be the machines that make stuff. Because we kind of forget that. I like how in that video, he talked about paper cups, and you might think how is that? It's not machined, it's paper. But the mold is machined, or the machine that makes the paper cups is machined. And China is really good, have gotten really good at that. You can buy. I saw they have machines now that wind electric motors that do that complex winding with the enamel coated copper wire for $18,000. You can buy this advanced CNC motor winding machine. So I think some of that might come back, where we actually start making our own machines that make machines. Again, right now, the things that have not left America is mostly aerospace, or defense, because it just can't, it's for national security. So that's already kind of here, but even that's getting better. Anduril is one of the companies I listed in the course description. They are a startup in Costa Mesa, California, and they actually just got the contract from the U.S. government for our autonomous fighter drone. I can't remember the name of it. I think it's called Barracuda. Oh, no, that's the missile. Anyway. Do you remember?
No, I was going to say they have a sister shop for their marine thing right next to the nuclear submarine base down in Connecticut, and they're running their...
for Anduril?
Yes.
Oh, cool.
Running their
that autonomous
sub drones
wow.
on that base.
That's so cool. So even defense actually is growing too. That's really cool to know.
Yeah, my mom mentioned that it's a real struggle right now. She works for General Dynamics, and they work on the nuclear submarines, and it's a real struggle because everything's made in China, so you have to make all the parts here, obviously, because it's classified. So it's been a struggle for them to keep up with the manufacturing for the parts that they need there.
Yeah, it does. It's hard. Yeah, we don't realize, but even if we try to just maintain one industry like aerospace, there's so many things that we take for granted that are then dependent on that. Just the screws for making the machines that make our parts, or whatever. And so we are still dependent. And I, on the one hand, I'm kind of a believer in an interconnected world, and that helps to maintain peace. There's, but on the other hand, the reality is you kind of do have to at least have an emergency capability, and I think that's what COVID showed. So honestly, it's actually not a bad trade. Honestly, you can make pretty good money now if you just open a machine shop. Okay, I will caveat that by saying it's better if you make your own product. If you just do contract work, you can actually still make pretty good money if you're smart about it. But it's even better, you get the full value, of course, if you're making something that you designed yourself, your own products, and doing direct-to-consumer, direct-to-business, yeah.
Do you think that as the price comes down in terms of maybe 3D printing metal parts?
Yeah.
Where the finishes are easy to do, and will that make all this obsolete?
I don't know. I would say that generally, it's funny because what's kind of happening is that they just keep both progressing. So yes, 3D printing gets better, but so does machining. And machining is just kind of inherently always ahead of it. It's always, at least right now, it's still faster. It's just always faster. It's always cheaper per part. I don't know. I don't know if there's going to be a time where 3D. One of the old machinists that I first met, he really thought 3D printing would eventually get rid of machining. But I don't. It's nowhere close. I don't know.
Printing metal, there are.
Yeah, I know what you mean. I know what you mean. You're right. Even with metal, yeah, we're still nowhere close. So I don't know. Okay. Yeah. Okay. Any other questions? All right, guys. Well, thank you very much for coming. Please feel free to come say hello. Be happy to meet you, and we'll see you on Wednesday. Thank you.